Hello, everyone. It's a great honor to be here to introduce our work in ICPP. And the title of our work is Dubhe Towards Data Unbiasedness with Homomorphic Encryption in Federated Learning Client Selection. And I'm the first author, Shulai Zhang, and all the authors are from Shanghai Jiao Tong University. So our work is focusing on federated learning, and as shown in this figure, in federated learning, a portion of clients are selected in each round and trained on their own local data. And then these clients send their updated models to the server, and the server aggregates the received models and send back a shared model to all the clients. So there is a great amount of security promise here, because there can exist an attacker who can analyze, infer, or reconstruct the original data from users using the weights or data distribution information from those transmitted messages. So in recent research, a technique called homomorphic encryption is widely used by researchers to help protect the security of clients. Here is a simple example of homomorphic encryption. On client 1 and client 2 have message A and message B separately. If they send these two messages to the server directly, the server or the other third parties can learn from those plain texts. But using homomorphic encryption, those two clients can encrypt the messages with their public keys and then send those encrypted messages to the server. And the server can then aggregate those messages directly. The server add those two messages directly and without knowing what A and B really are. And in our work, we are using homomorphic encryption to alleviate the problem of statistical heterogeneity in federated learning. And the statistical heterogeneity is a typical problem in the scope of federated learning. And there are three aspects of statistical heterogeneity. And the first one is the local data skewness, which means that the local data on each client is biased. And the second aspect is the data discrepancy among clients, which means that the data distributions among clients are different. And as shown in this figure, we use the parameter EMD to analyze, to evaluate the discrepancy among clients. And the larger the data discrepancy among clients, lower the test accuracy. The global data skewness is also an important factor that degrades the performance of federated learning, because the distribution of participated data in each training run will also be skewed when the global data is skewed like this. We also mathematically demonstrate how would the statistical heterogeneity affect the performance of a model by deriving the weight divergence here, which is the difference between the model weights trained in a federated learning system and the optimal model weights on the balanced test data set. The weight divergence is bounded by several terms, and the first term here represents the data discrepancy among clients, and the second term here represents the influence of global data skewness. PL here is the local data distribution of each client. PO here is the population data distribution, which is the distribution of participated data in each round. And PU here is the uniform distribution, which represents the data distribution on an unbiased test data set. Client selection method directly influence the population data distribution, thereby influencing the term 1 and term 2. The baseline client selection method is the random selection method, which means to select the clients randomly in each round. And the optimal client selection method is the greedy selection method, which means that the clients are selected one by one to minimize the gap between PO and PU. However, the greedy selection method breaks the security promise in federated learning. And this is because it has to know the data distribution of all clients. And in this work, we'll use homomorphic encryption to protect the user's data information, and our target is to minimize the discrepancy between the population data distribution and the uniform distribution. Now let's move on to the design of Dubhe. There is a parameter search procedure at the very beginning, and there are two parts in each round of federated learning, which are the client selection part and the training part. And within the client selection part, there are two main modules, which are the registration and probability calculation module and the multi-time selection module. We will introduce the registration and probability calculation module first. We developed the concept of registry, and the registry encodes the client's data distribution information in a one-hot manner. And in classification problems, specifically in our work, the registry encodes each client's data distribution by its dominating classes. And here are two samples for a better understanding of the concept of registry. The first data distribution here has category 1 dominated, and the second data distribution here has category 1 and category 2 dominated. Thus, we flip the 0 here to be 1 and the 0 here to be 1. Those two registries can tell the system what kind of data distributions do these clients have, because they have recorded enough information in it. Now let's put the concept of registry into the real system design. In each round, clients encrypt the registry with their public keys and send those encrypted registries to the server. And the server then aggregates all the registry together to get the overall registry and send back the overall registry to the server, to the clients. And the clients can decrypt with their private keys and do the probability calculation. And with those probabilities, those clients can decide whether to participate in this round of training by themselves. We compare the training performance of different client selection methods on various data sets, and in most cases, Dubhe can reach the performance of the optimal greedy selection method, and the random selection method is the worst. And here are the results on the feminist data set. And we also visualize the distribution of participated data in each training round. And as we can see, the data balancing performance of Dubhe is approaching the performance of the greedy selection method. And now let's move on to the design of the multi-time selection module. The main idea of this multi-time selection module is the same as the registration part. In each round, our clients send their local data distribution to the server, and the server sends the aggregated data distribution, which is the encrypted population data distribution, actually, to an agent. And the agent is responsible to record the population data distributions, and this procedure can be repeated for several times, so that the agent can pick a combination of clients with the most uniform data distribution. As we can see in the results with multi-time selection, the EMD is decreasing with larger H, which means the population data distribution is reaching the uniform distribution, and the model accuracy also increases with H. The performance of Dubhe can be significantly degraded by the sparsity of registry. Here is an example of the overall registry and its corresponding participated class proportion. And the number in each block here represents the number of clients who belongs to the corresponding user category. And for example, in this block, there are 3 out of 1,000 clients who have class 2 and class 9 dominated. And notice that here, There are no clients who have class 8 or class 9 dominated. So now, as we can see, there is a deviation from the uniform distribution in the participated data distribution. So the sparsity of the overall of this overall registry is the primary cause of this deviation from expectation. Now let's come to the conclusions. And in this work, the impact of data skewness on the performance degradation in federated learning is mathematically demonstrated. And we also propose Dubhe, a proactive client selection system to balance skewed data. And it has three main advantages. First, it is pluggable, adaptive, and robust to various FL settings. And second, it has negligible encryption and communication overhead. And this part is also explained in detail in our paper. And the third advantage is that Dubhe improves the training performance without bringing security threats. So that's all of the presentation. And thanks for listening. If you have any questions or comments, please contact. Thank you.